for the past summer. All of you, please welcome and feel this a momentous occasion with you because you all worked really hard to get to this point. We all worked hard trying to figure out the best design for this year's competition. All of you are starting on your process, your journey as engineers. And through our Airborne, I hope you gain the experiences, make the friends, and make various lifelong memories in your journey for next year. All of you who are team leads, some of you are leaving or graduating this coming year, again, applause to yourselves for being team leads and leading this team into this momentous occasion and to the coming journey that it will be very, very fun, very interesting, and very worthwhile. So, without further ado, I am proud to introduce the first preliminary design review for 2025-26. And let's get started with our organizational overview. So, for those who are new here, this is your first time, hi, welcome. I'm Anastasia, I'm the captain of our Airborne. And PDR is essentially this entire review, this process of the design of our vehicle over the past couple months. We had to make a lot of tough decisions already. How do we go about designing such a complicated and heavily optimized vehicle for this year's competition? And if you have no idea what I'm talking about, that's okay. We just build airplanes, and I think airplanes are cool. This is today's schedule. So I know we're starting a bit late. Sorry about that. I had to set up the live stream. So if you all want to go back and watch this on YouTube at some point, you'll be welcome to. The links in the announcements of Discord. So we're going to go through the organizational overview, the system requirements, and a little bit of debriefing from the RADA program. So hi all for RADA. Thank you again for being part of our program. I hope you all enjoyed it. As you see, you'll see some RADA members presenting in a little bit. So much applause to you guys. We're also going to go about mission overview. What this year's mission is about. The various analysis we have to perform to figure out what do we want to design around. And then through that, the actual design of the vehicle, from everything from aerodynamics, propulsion, aerostructures, and the actual mission design, as well as how you build the airplane. And then we'll finalize it with a little bit of business that we've been up to, with really cool events and really cool future things that we'll be doing, and some conclusions and questions. Now, PDR is one of those things where you are more than welcome to ask questions. This is where you get to know your fellow team members. You need to learn some names explain the actual organization as a whole.
All right. Hello. So if you guys don't know me, my name is Mahadi, and I'm gonna go over how our team is organized, and then a bit about the documentation. So first, we're gonna start off with the team hierarchy. So you might have seen all these people before. These are basically our team admin and leads. So on top, we've got Anastasia, our captain. Then we've got our three, I would say admin. We got Arsh right over here, our chief engineer. We got me, Mahadi, the project manager, and Sharish, who's over here, it's operations director. So basically, us four, we are in charge of basically organizing the team, the meetings, making sure everyone is staying on track, that everything is getting done, and that all of you guys, the new members, feel welcome and are able to learn as much as you guys can. So next, the next two rows, we've got our team leads. So we've got Dia and Huzaifa, who are our air structures leads. We've got Joel, who's our mission specialist. Don't know where. Yeah, there you are. Okay, we've got Enrico and Andy, aerodynamics. Shravani and Sai. Shravani's not here, but Sai's over here, who is our propulsion leads. And we got Sean and Sean. Sean G and Sean M, our manufacturing leads. And we've got Evelina, who isn't here today, who is our business lead. So that is basically our overview of our team leadership. Yeah, so if you guys wanted like a little visualization of how the team is organized, this basically kind of maps it out. We've got Professor Tomorrow, who's our faculty advisor, that's all out there, and then our pilot, who this year is also Anastasia. All right, now to documentation.
So me and Somitha here, we're both members of RADA this year, so we were able to experience the new member onboarding process essentially. I mean, before I continue on, first of all, I'd just like to say, if you want to take a picture, I mean, I know I look amazing here, so if you want to, go ahead. But nonetheless, what even is RADA? What's the structure of it? What were the good, the things that we could improve on? And yeah. So, what is the Rutgers Airborne? What is the Rutgers Airborne Trainer Aircraft Program? It's essentially our onboarding process for new members, prospective members. It's a 2.5-week long phase where members are introduced to all of the sub-teams, so aerodynamics, mission, aerostructures, et cetera, et cetera. They gain hands-on experience with what these teams actually do, so they learn the softwares that they use, how they document their things, stuff like that. They also get to meet with the leads one-on-one, ask any questions that they had. And by the end of that 2.5-week process, they're let go, they're free to choose whatever sub-team they want to work with for the rest of the competition time. So it's broken up into 5 meetings. The first meeting is just an information session, similar to this, but less in depth. It's mainly about how Airborne is actually run, the competition rules, how people get to competition, and sub-team introductions. So where sub-teams will introduce themselves, say what they do, and why you should be with them. The second and third meetings were more so hands-on. That's where members had an hour with each sub-team to learn about what they do and get experience with their software. So things such as SolidWorks, FLR5, ECalc, etc. They started working on simple projects, nothing too crazy, just to learn what they do. And then the fourth meeting was where they got to choose which sub-team they wanted to learn more about for the entire 2-hour meeting period. They went more in depth with what that sub-team did. So more so like going more in depth with analysis, more in depth with CADing, stuff like that. And then day 5 was kind of where we shifted towards our competition aircraft for this year. So we were working on sizing our aircraft and stuff like that. So each sub-team did their own activities for these new members. So aerodynamics firstly started with slides on theory behind how planes fly, essentially. And they were giving their members tasks to do hand calculations, which they'll also be doing for things like coefficient of lift and coefficient of drag. And they were also presented to the software that they use, XFLR5, and were able to do wing or airfoil analysis. Aerostructures, they provided their members with some CAD models that they were able to make themselves. So they actually went into SolidWorks, chose a few CAD models to make, and made them themselves. Mission presented the problem that they had to solve last year, which was making exterior fuel carriers to be held onto the outside of the wing. Members had to create a problem and a design that they would actually show to Joel about how they would solve that problem. Manufacturing was a lot of safety stuff, and members got a tour of what we call the cage. Furthermore, new members were actually able to build the RADA aircraft. They were able to build the structure of it, monocoding it, stuff like that. And propulsion demonstrated their primary software, which is ECalc, and they allowed members to play around with propulsion systems. Yeah.
Thank you, Darian. Next, we're going to talk a bit more about the good, the bad, and some improvements that could happen during RADA. So something that went good is that everyone learned the structure of Are You Airborne? Activities were generally engaging. I personally did manufacturing, and it definitely was really engaging. I'd really like to shout out both Sean's for being the deputies, as well as Adrian, as well as Sharish, who also popped in quite a bit into manufacturing as well. Yeah, and it was really nice to talk to all the leads, as well as new and current members as well. And it was mostly organized, and we're going to talk a bit more about that when we get to the improvements. So, some things I would say something that could be improved upon, or some things that are bad, or something
Sharish and Joel to the stage. Welcome, welcome.
Hello everyone, you saw me in the team overview introduction, and I'm Sharish,
Joel.
and we're going to go over this year's mission and all that it encompasses. So let's get started. So obviously you guys know that we're designing aircraft for the design build flight competition, and we need to build an aircraft that'll conduct charter flights, and it's going to be a bush towing aircraft that'll like fly a banner and have passengers in it. And what we're trying to do is to maximize the mission score through these different missions, and the aircraft should also like demonstrate that it can fly, it can have high lift endurance, have payload efficiency, have good stability, and it should be able to be rapidly assembled, and it's all covered within the general mission scope that we'll go over soon. So that is an example of a bush towing aircraft that you'll see around Rutgers, and that's basically what we have to build this year. So some general mission requirements this year something newish that's been added is a rated aircraft cost, which is a variable dependent on wingspan, and it basically has sets a maximum wingspan as 5 feet, but also sets also a minimum wingspan of around 3 foot to maximize the score. And the score affects mainly like the mission to like scoring and is vital to that mission scoring. And then on top of that, we have the ground mission, which is the assembly and the ground demonstration. You have mission 1, which is no payload and basically a flight test. You have mission 2, which is the passenger and cargo mission, and mission 3, which is the banner towing mission. So to go more into specifics about mission, let's have Joel start off.
So it all starts with the ground mission, which is basically a analysis or a test of how fast you can get your plane configured and ready for flight. So the ground mission takes place in am I blocking the screen? The ground mission takes place in a 10-foot by 10-foot box. We'll call it the mission box. And on the edge of this box, there's a start-finish line, because you'll be starting, the ground crew member, who is the person who is configuring the plane, will be starting outside of the box, and then we'll be configuring the aircraft inside of the box. So before the timer starts, the pilot will be verifying the flight control surfaces just to make sure they're all active and working. Then the ground mission judge will start the timer. The ground crew member will run from the start-finish line into the box to assemble or to install their payload into the aircraft. So there will be cargo and passengers laid out near the aircraft, and the amount of payload is equal to the maximum amount that you declared during technical inspection that you can carry in your aircraft. So under the stress of time, you install your cargo and passengers as quickly as you can, and then you run back to the start-finish line, and the timer is paused. The next part of the ground mission is the banner installation. So the judge will yell go again, and then you cross the start-finish line again, go to your aircraft where the banner is also laid out next to it. You uninstall all the passengers and cargo from the aircraft, and then you install your banner into the stowed configuration. Then you make a dash out of the box and cross the start-finish line when the timer will be stopped. To conclude the ground mission, the ground crew member will hold up the aircraft in a nose-up orientation, and then the pilot will deploy the banner just to make sure your mechanism actually works. So, the first flight mission is mission 1, and it pretty much goes the same way every year, but to explain it for those of you who don't know, it basically revolves around this flight loop, which is it starts at a 1,000-foot runway, you take off upwind, and then you make an oval shape that's interrupted by a loop on the downwind leg. So, as I mentioned before, the runway is 1,000 feet, and here you have to complete 3 laps in 5 minutes. If you do that successfully, you get 1 point. If you don't do that successfully, you get 0 points. So you have to pass mission 1, and then after you do that, you will be available, or you'll be eligible to complete the other 2 flight missions.
Mission 2 is where we get a little bit more complicated, where it's the charter flight. So the main aspect of this mission are the passengers and the cargoes. So
seen by the equation on the bottom, the more laps you complete, the more points you get. Another thing that's scored is your RAC, or rated aircraft cost, which, as mentioned before, is a function of your wingspan. So smaller wingspan, more points, more laps, more points, and then finally, a longer banner equals more points. So, after the first upwind turn, the banner is deployed, and then you complete your as many laps as you complete, and then after it crosses the finish line of your final lap, you release the banner, as in you cut it off from the aircraft entirely, and it falls to the ground. So, some requirements about the banner itself. First of all, it has to have a minimum length of 10 inches. If you go with this minimum length, you'll be constrained to a minimum, or just a height of 2 inches. If you go with a larger length than 10 inches, you will have to have your height of the banner be at least 1/5 of its length. Also, the banner has to have the team's university name and/or logo on both sides, and it has to remain in a vertical orientation throughout flight. This is so that the judge and the other audience on the ground can actually see the banner and what it says while it's in the air. Some other requirements: the banner has to be stowed externally on takeoff. So it has to be stored compactly so that the banner is not interfering with any flight control surfaces, or if it's not like it can't be striking the ground on takeoff and things like that. Another requirement is that it has to be durable enough to not sustain any visible damage when it's released or when it's in flight. So yeah.
Well, thank you guys.
Thank you.
All right, now we heard about the riveting mission this year. How do we actually go about determining what we want to know more about? So, some of you might have seen me locked up in a little cubicle in the graduate offices. So, you might be wondering, what was he doing? And for those who were with me on mission 2 and mission 3 and ground mission sensitivities, look at you guys. It was interesting. Definitely very math heavy. So every year, what ends up happening is when we go about sensitivity constraint analysis, it's a new set of requirements, a new set of missions that make you have to ponder what is relying on, because not only are you varying each parameter or each part of the sensitivity, which I'll explain what that means in a second, not only are you varying those, but you also have to figure out how does that affect the performance of the vehicle. So it's a very heavily coupled system of motion and score to figure out what is the most effective thing to prioritize when designing the vehicle. So we're going to start off with sensitivity analysis. So sensitivity analysis is a type of analysis that allows you to figure out what parameters is your design most sensitive to. So what is a parameter and what does sensitivity mean? Well, let's say we have the cargo, we have the passengers, the ducts, and we also have the banner length. If you vary those 3 things, that will change our score. So the question is, which one varies the score the most? Then you get even more complicated factors. You have the efficiency factor from the battery, and then you also have the rated aircraft costs. Those affect the actual performance of the vehicle. What about how much battery you have? How big are your wings? How fast or slow your aircraft is? Can it maneuver very well? Should it maneuver very well? Those are all the questions you're trying to figure out when determining the sensitivity analysis. So the overall design of it is a MATLAB program that takes in these scores, these scoring requirements, and then coupling that to a performance, basically a series of equations of motion coupled to additional differential equations that govern the performance of the vehicle, taking that big soup and now actually boiling it over the stove and actually figuring out what is the aircraft most sensitive to. So when we talk about the sensitivity, we're varying the little change in parameter to figure out the So we take all that and we just iterate upon it multiple times until we figure out and we have an actual diagram to explain to us engineers what do we want to design around, how do we want to design it. So what are we assuming and what are we figuring out? Well, after analyzing and taking a lot of your guys' input, so thank you for all of you who worked on sensitivity analysis and for your wonderful code, because we were able to figure out, okay, well, we want to assume certain parts are constant. Let's say we assume we're in cruise velocity, or at a certain point are we turning, or at a certain point are we inclined. You take all those concepts, and then you vary each of the little parts of those motion, those performance equations. Battery capacity is the toughest one, which propulsion was able to crack, so proud of you guys for that one. Bank angle, which determines basically how small a turn can we physically take. Do we want to take a nice, long, gentle turn, or do we want to take a nice, fast, quick turn? Which you might guys have an intuition on, and that intuition will be proven mathematically. Then we also have wing area. How much lifting area do we want? Do we want lifting area to maximize, but oh no, if you have a lot of lifting area, a lot of wing, you may have a lot of induced drag, or you may have some other caveats attached to that. Then you have a wingspan. Wingspan matters this year in the sense that we can't just maximize it, our score is attached to maximum, or minimizing it rather. If you minimize the wingspan, you will in theory get more score. We'll prove that mathematically as well. And we got ground mission time, we got passenger count, cargo count, and ultimately the banner length. All these little things, when you increase them or decrease them, change the performance of the vehicle, which makes it such a complicated problem. And when you solve this complicated problem, you get a graph like this. Well, a lot of lines that kind of don't make sense initially, but when you dissect all those, you'll figure out there's a lot of useful information in there. So, let's take a look at it, for example. See this, well, technically I think it's a purple line. Is it a black line or a purple line? It looks black, I don't know. I made this up to it, yeah. So, when you look at the black line, that's your banner length. Look at what a 0.05% change in that banner length will do for you. Look at the massive jump. It goes up another 0.05% of the score. That's for like every 5% of a foot. So imagine what 20 feet does, 30 feet, or even 40 feet does. Those are massive changes in your score. What's about that green line that looks kind of quadratic? Well, that's your bank angle line. You'll see that you want to take a really high bank angle because you can make the turns a lot smaller. You can decrease the total time for your lap. And then you also have, interestingly enough, the wingspan in that red line is going downward. Is that a bad thing? No, it's not a bad thing. What we actually see is that if you decrease the wingspan, you'll see a jump in your score. And if you take the average of that, you can also see it reflected on the opposite side, where the average slope increase of the cargo is also beneficial. So the question is, after all these things, and you see lines that are closer to zero, do those lines matter? No, because you don't give as much of a jump in score. So, what are the primary conclusions? Make a hell of a long banner is one of them. The second one is make a super maneuverable aircraft, more maneuverable than you've ever designed before. Have a wingspan, try to minimize that. How do you minimize a wingspan and make it more maneuverable without, introducing very unstable effects for the vehicle? How about cargo? Cargo, you're going to increase it so much, you have to tow a ton of cargo, or a whole bunch of it. And remember, you need, for there's a ratio, where you need at minimum at least 3 passengers per cargo. So you have a lot of cargo, you're going to have 3 times as much passengers minimally. So all those things now tell us, along with trying to put the cargo and passengers in the ground, we should try to assemble it into the vehicle. You the acceleration inward that causes an object to go into rotation. So if you have a high enough load factor, which means a high enough bank angle, and you want to relate that, you can relate it between the wing loading and different parts of the aircraft, such as the actual velocity of the vehicle, the drag of the vehicle, and other parts like the dynamic pressure and the aspect ratio. So once you figure out, you can create a relationship between the actual load factor while banking and turning the vehicle. And now you have a relationship just for that. Then you have a relationship for wing cube loading. Essentially, it tells you how easy is it or hard to fly the aircraft. So on this end of the spectrum, you got paper airplane. On this end, you got like an F-18. So where do you want to be? Well, competitively, you're like over here. Daedalus was somewhere over here. Scorpion 2 years ago was F-18. But it made it easier to fly, a little bit easier. It allowed us to be able to control the vehicle much more smoothly in flight and figure out how we want to go about actually optimizing the mission. So that's an important constraint. How easy is it to fly? Then you have the thrust to weight ratio for a desired cruise speed, which is almost exactly like the load factor version, except without the n squared. And we can talk about the aerodynamics of why that is, but I won't go too deeply into that. Just know that this relationship relates the wing loading directly to thrust to weight, and through that to velocity. So this is the part that kind of tripped me up for a bit, and still trips me up. In fact, it trips Professor DeMora up, which he's like the aerodynamics guy here at Rutgers. So it trips him up, and it trips up Baru, and even Knight, and pretty much every professor. Then you know we're kind of cooked. So how do we actually determine the big banner that's super long? We want to make it super long. How do we actually figure out what kind of effect does that have on the constraint? Because obviously that has a constraint on the vehicle. So what we did was, let's say this banner, a banner, or think of a flag really, like a flag on a pole. It flutters about, back and forth. What if that fluttering was like a sine wave? So what we did was, I talked to Professor DeMora, he said, well, we could force it like into a sinusoidal motion, and we'll create a relationship for that. So through a bit of math, really cool math, so for my aerodynamics people, I hope you get to experiment with this at some point in the future because I'm really excited by it. We developed a relationship that determines how much the banner will oscillate, and from that, determine the actual average drag from that banner. And when you actually put it into a graph, it looks something like this. Now, is it completely accurate? No. But it's better than what we call a flat plate approximation, which basically says if I took a really big old plate and put it into what we call angle attack, or how much angle between the air it's moving, we'll then see that the drag looks like 40 pounds, which we know is not true because USC did it with like a 30-foot long banner, and they did not experience that much drag. So we have to create something more accurate to determine that. So we did a little bit of trickery, a little bit of cool math, and then from that, we determined the actual constraint. So over here, this is the constraint diagram. Essentially, you want to be in that white regime over there. If you're in the white regime, above all these lines, you're in a good zone. It's a good one to pick. So the biggest constraint is that top little blue line. That one there, that's from the drag of the vehicle. So that tells us that, wow, we need a lot of thrust. So we need a lot of thrust, so at least minimally a thrust weight ratio of 1. And we don't want to go too much higher for wing loading, because if we go too high, we'll have too much force on the wings, and that usually ends up resulting in shorter wingspan, ends up in a more unstable vehicle for what we were trying to work with. So, and you also can see the wing cube loading relationship. So the higher the wing loading, the higher the wing cube loading is, so the more difficult to fly. So, taking those relationships, we pick a point. And this point happens to be, you can get that for me, a thrust to weight ratio of 1 to 1 pounds, a wing loading of 1.9014 pounds per foot squared, and then the wing cube loading of around 10, which is
should be focusing on. There's the structural consideration, the aerodynamic consideration, and the manufacturing consideration. Usually, for the past 2 years, as I mentioned, we've done a monoplane. The thing is, one of the actually cons, I'd say, for doing a monoplane is that for one wing, you have only one spar running across the whole wing. Now, what that does is that you have a lot more stress, shear, and all the strain being applied to just one wing specifically. However, if you have a biplane, it basically distributes that load distribution between two wings. And you can actually have less shear, less stress that actually is being applied when you're in flight. Another thing for doing biplane is that it actually decreases our bending moment. So if we don't have a lot of moment, that means we won't have a lot of flutter, which I will go into, and also structures we'll be mentioning a bit later on, is usually for biplane wings, there's also struts. So like some sort of rods that are connected from the top wing and the bottom wing, right? That actually help for actually increasing the chance of structural stability of the aircraft. So that aerostructures will go on there after that next slide. All right, manufacturing considerations. This is the first time in, I'm pretty sure, airborne history that we will be manufacturing a biplane. It will have its complications, I will say. That's not something that I will say is going to be coming easy to us, right? Best part of the manufacturing is that we have a bit more leeway to actually work with weight. So the number of passengers we can add is completely up to us based on how we determine the CG of the aircraft. And we have a bit more leeway because if we have two wings in the forward fuselage, front of the fuselage, then we can shift around the weight as much as we want. Alright, next is aerodynamic consideration. Alright, this is where kind of comes off like out of my, I guess, specialty, but I'll try my best to explain it. So, from an aerodynamic perspective or standpoint, the biplane helps us kind of cheat the system a bit. How does it let us cheat it though? So, by stacking two wings on the fuselage, what it basically does is that it effectively increases the aspect ratio without actually increasing the span of the aircraft, which we want. That's good, because it'll give us a really high nominal score for the RSU limit. And I know what you're thinking that, oh, why, a lot of the aircraft colleges will be doing that too. However, we have a bit of flight heritage in our advantages, and we have a lot of people here that are absolutely great at doing the job. Now, if you increase the aspect ratio without increasing span, the interference between the wings, so this is a picture that I quite literally did in 10 minutes today. I did not have a lot of time refining it. This picture shows the grid convergence of the difference between a monoplane and a biplane. So what is grid convergence? It's basically a mesh created between like a surface or a surface that you can tell what is happening between. For a monoplane, there's one wing, right? So if the stream is going across, it's pretty normal. There's nothing much going on here. But at the trailing edge, there's like a lot of work
about between 10 to 15% is like what we're aiming at. A high CL at 0 degrees and a 2 degree for angle of attack is probably just what we're aiming for. High coefficient of max and an angle of attack stall are good for stall progression. Obviously, we don't want to like angle of attack that's too low and then we start stalling. Some methods that we like considered is we looked into past TBF competitions, which had similar constraints, and we just used that. And for 2020, we actually had a really similar competition, so that's kind of like where we like compared values for. And for the decision matrix, that's where we found all our like potential airfoils. We just took them from last year, and then that's how we found out which airfoil we're going to use for this competition. For analysis, we for expo we use expo 2D viscous analysis. So that's just like a method we use on the application. And with that, we use batch analysis, subsonic flow, and a specific Reynolds number, depending on like if we're using a horizontal tail, vertical tail, or the wings. So we use a 400,000 for our Reynolds number. And how do we evaluate like how like both what numbers we want? We use quantitative design matrix. So like with a matrix, we were able to like figure out what exact like, values we need. And the criteria is listed right here. CO versus TD at 2 degrees, CO max over CD min, 2D lift slope, CO max, stalling of attack, airfoil thickness, coefficient lift at 0 degrees, and a coefficient lift at 3 degrees.
So as Max said, we tested a bunch of airfoils, mainly from flight history, things that worked for us in the past. So some of that include MH112, Clark Z, Clark V, and a whole lot more. We ended up choosing MH114 mainly for its excellent lift characteristics, its lift to drag ratio, which is good because you want to be able to fly and not be dragged. Its stall characteristics, so basically how well can you rebound from a stall given that you do stall. And since it's cambered, it does produce a little bit of lift even at an angle of attack of 0 degrees, so that's good, especially when you're taking off. The only con is the trailing edge at the end. It might be too thin, however, with a long enough cord, it should be thick enough. Thickness is dependent on cord length, so the bigger your cord, the bigger your thickness. And then these are the graphs for MH114. So we have the 2D lift slope is essentially how much your coefficient of lift changes for a given alpha. So we want that to be positive. So as you go increase your angle of attack, you produce more lift. There's a beginning linear portion, and then as you go on, it kind of becomes curved. That's what we call our stall progression. We don't want that to be abrupt. Again, that aids in how we can retrieve our aircraft, given that it does stall. So given that it's curved, it's easier to retrieve it back from stall. Its maximum coefficient of lift is about 1.8. And yeah, the drag polar curve, that is also good. As you can see, we have really high coefficient of lift. And as you look on the x-axis, it's a fairly low coefficient drag. Again, that's good. We want more lift, less drag. As you can see, like imagine a tangent line to that graph. You would have a slope of 0 right around the maximum coefficient of lift, and then it starts decreasing. So that kind of means that our drag forces are increasing while our drag forces are increasing while our lift is decreasing, which that happens at our maximum angle of attack, which is about 14.5 degrees, which is good because we're not going to be flying at 14.5 degrees for a long time. We're mainly going to be flying around 3 degrees above the horizon. And yeah.
And so as mentioned before, the aspect ratio and wing load that we found to be optimal was 4 and 1.9. So this is because of the low wingspan that we required. And because we basically know our takeoff weight is going to be 15 pounds, given that we want our aspect ratio to be 4 and wing loading to be 1.9, we're essentially locked into a pretty narrow range of what our wingspan and the corresponding core take is an aspect ratio of 4 to, which meant that the amount of values we had to test was pretty limited, luckily. And the analysis we used XF Polar Fly BLM2 basically with the quantitative decision matrix. And so the sizes that we found to be most optimal was a 11.9-inch cord length and a span of 48 inches, which did give us an aspect ratio of exactly 4, and the wing loading of almost exactly 1.9. And so even though our testing range for gap to chord was only 0.75 to 1, the gap to chord that was most dominant was actually smaller at 0.625. So we did an XFLR5 analysis on the two wings, and it is shown here that there is no stagger provided no benefit to the lift to drag ratio of the wings. So for simplicity and for this first prototype, no stagger ratio was considered. And as you can see, wing 3 is the one that we chose. 11.9 chord, 4.48 span, and you have as the highest score. So that wing is our wing now.
So this is wind tunnel test from NACA. This gap to chord ratio for a specific angle attack, and then the stagger for angle attack. As Federico said, we didn't really use any stagger. The lines are, as you can see, over here, they're really close together, so there's not really much of a difference for the actual stall angle attack, as you can see. We said the higher gap to chord ratio decrease interference and improves lift, and we won't lift. Yeah.
So the most important part one of the most important parts about the biplane design is the gap to chord ratio. That pretty much determines how much interference the wings have with each other. So this is a graph that I guess I should start actually with Monk. He's the biplane goat, and he introduces two efficiency factors based on either the geometric angle of attack or the camber of the airfoil. And these efficiency factors give you a lift reduction or a penalty. And if you look at the graph, B naught, what we're calling B naught, is the top line. It's higher. If it's higher than when it's multiplied against the lift, then it is more efficient than B down here, which is a lower number. It takes more of a lift penalty. So highly cambered is good. And the gap to chord ratio, of course, we would like it to be 1 or a little bit higher than 1 to minimize the interference of the two wings so that we don't take too much of a lift penalty. But because having a high gap to chord ratio means a big fuselage, that's not good for aerostructures, and we have to compromise. So we take something pretty small, gap to chord of 62.5%, fuselage and structure reasons. And if you're interested in the exact numbers, there it is. B naught's 0.88, kinda. B is 0.77.
So when doing the initial tail sizing, a few parameters that we take into account is the aspect ratio as well as the tail volume ratio. And in terms of the aspect ratio, we want to ensure that it is small enough to reduce the risk of a tail stall, but also big enough so that it can respond to any disturbances. So in terms of the horizontal tail, we figured out that our range between 3 to 5 is what we're expecting. As well as for the vertical tail, we're looking at aspect ratio between 0.9 as well as 2. And then in terms of the tail volume ratio, which is for the horizontal tail, we're looking at about 0.4 to 0.7, and the vertical tail is 0.025 to 0.075. And in terms of the tail volume ratios, as displayed up here using our formulas, varying the parameters such as our moment arm, the area of the horizontal tail or the vertical tail, as well as the actual wingspan of the aircraft, of the wing, as well as the geometric mean chord, as well as the area of the wing are what we use to try and get a value between the ranges that we are looking for.
So for airfoil, we analyze symmetric NACA airfoils. So essentially, if you see the x-axis on this diagram, that's what we're trying to find it symmetric about. Why do we want it symmetric? That's because it produces no lift at an angle of attack of 0 degrees, and that is optimal for stability, which is what we want. We did use a decision matrix to choose this airfoil. We prioritize a high coefficient of lift and stall angle. We do want the tail to be effective in the case that the installed. And we obviously prioritize higher thickness just for ease of manufacturability. And what we chose was the NACA 0015.
So the tail is at some distance from the wing, call that the underarm or the open arm. These are the equations. They're from Snorri. What they do is they minimize the emitted area of the tail surfaces and fuselage, and that gives us less drag, or the optimal drag, so the least. Yeah. So we got a sheet. We altered the volume ratios. Expect our fuselage to have a diameter of like 8, and that's what the sheet spit out. And it was different for the horizontal and vertical tail, but it's not that different. So for simplicity's sake, we just make them the same. That's a pretty typical thing to do. So with that spreadsheet that Federico made, it's got a bunch of equations from Snorri, like that one from the previous slide. So we pick some parameters that the spreadsheet spits out, and then we put it in XY5, and we make a plane, and we estimate Cm naught, Cm alpha, and the trim angle. So Cm naught is the coefficient of pitching moment at an angle of attack of 0, and we want that to be positive so that we can trim at some positive angle of attack so that we can fly our plane. Cm alpha is the slope of this graph. So the slope should be negative, so that means that if you pitch down from a disturbance, then airplane must go up, vice versa. And I don't think I need to get into the specifics of the analyses, but we did fixed lift 3D. We set nominal CG at about quarter chord, and our gap to chord ratio in this one is 0.625, so like we expect. The static stability criteria is Cm naught, once again, has to be greater than 0. Cm alpha has to be negative, so the slope has to be negative, and the y-intercept has to be positive. So you can see that these configurations, for the most part, do match that. So after iterating through tons of values for the area, span, chord, this is what we got. So we ended up with a span of 28 inches about, chord of 7 inches about, area of about 200 inches squared.
So this is the initial horizontal tail slicing. So we used the VLM2 type 2 analysis with a varying angle of attack from -3 degrees to 20 degrees. And we used X4 R5 to provide more conservative values of Cm naught, and Cm alpha. And we also used hand calculations to estimate the moment contribution of the wings. And in the table, these are the values we got for
Alright, this is the fun one. So we're flying a banner, so that if the crosswinds on the banner, that's going to make a lot of unfavorable yaw moments. So we do need a very good vertical tail. So it is the utmost priority of the aircraft, in my opinion, a very strong opinion. So for vertical tail sizing, we did the same thing like horizontal tail sizing. So varying the aspect ratio, varying the tail volume ratio, and then once we found a couple parameters, then we used XLR5 type 5 analysis, which varies the side slip or beta angle. So you see the aircraft, it does like rotates the angle. It's called beta. That's called the side slip angle. And the criteria for that is we want the yaw moment, the yaw moment derivative, or the slope with respect to beta to be greater than 0, and the roll moment with respect to beta to be less than 0. And that is the criteria for lateral stability. So nice equation here. It was also, to do the hand calculation, it was required to estimate the side wash contribution to the vertical tail, and that is given by that equation there. And once you solve that, then finding the Cn beta, or the stability derivative in terms of yaw moment for the vertical tail, is given by the equation below. After finding the values. So you see the table, that one is less, like, it's less than the hand count. And our final dimensions from a stable or a vertical tail flexibility, we found an aspect ratio of 1.9, an area of 95 inches squared, and a tail volume ratio on the higher end of 0.068. And I also calculated the roll. The roll derivative with respect to data, it's much smaller than the yaw derivative. All right, so the destabilizing parts of the yaw moments comes from the wing and the fuselage. It is given by that equation there. You have to go to a lot of tables to try to get a value, or not tables, but graphs, and you get and the calculated one that we got was on the order of 10 to the negative 4. So this is 2 orders of magnitude less than what the C and beta that our vertical tail provides, which is, I hope it says it's stable. I hope it's going to be stable.
So this is the aileron sizing. So we have ailerons on both sets of wings, and from the Goodmanson, I don't know how to pronounce that. So we use the strip integration theory to find the rolling moment derivative, and that's the equation right next to it. And from the Roxman, we estimated the average yaw, and we finalized that the aileron is 28% of the core wing, ranging from 60% to 95% of half the wingspan. And in the flaps, we also did the flaps of the same size, and we will be used on the inner portion of the wing from 20% to 50% of the half wingspan. So for elevator sizing, we use the Goodmanson and Nelson methods to estimate the elevator effectiveness, and we got the control derivative. So we got figure over there, we got a flap effectiveness parameter from there, and we decided on 40% tail core elevator based off like our previous flights. So the graph just shows the elevator effectiveness for the elevator area ratio. So if the elevator effectiveness that we chose was 40%, which is 0.4, respectively be 0.2. Yeah, for the elevator area ratio. So for yaw control, rudder sizing is one of the most important factors. So we used both the Nelson and the Rosecom method. The Rosecom was more detailed, and it predicted a higher rudder effectiveness. But then we just decided on using the 45% chord of the vertical tail. And like the diagram, those are the equations, and the diagram just shows what part of the actual tail is the rudder. Just how it.
So here's the data for so you have your change in roll, pitch, and yaw for if you deflect your control surface 10 degrees. As you can see, for roll, if you deflect your aileron and rudder, you will have a change in roll. It's not equal to 0, or if you deflect your rudder, it's not equal to 0 when you roll. So I didn't calculate that, but it's a fact. For yaw, for aileron, you can calculate adverse yaw, and we found it to be much less. It's less than when you deflect your rudder. The yaw moment when you deflect your rudder 10 degrees. Adverse yaw is when you deflect your ailerons, you get unfavorable yaw. And now for pitch, only the elevator. When you deflect your elevator, that changes only pitch, and you have a delta CM of much larger value than what you get if you deflect your ladder control surfaces. Here's our current aircraft on XLR 5. You have put a couple of point masses here. It's not as nice as the one on SolidWorks, but yeah. So we have some future projects that we're having is, we're gonna investigate maybe having a taper ratio or just not a perfectly rectangular platform for better wind want to delve further into the biplane configuration, and this may include redesigning or resizing. It depends on how well we fly and how well the first prototype goes. We're going to determine our CG envelope and mass properties once that gets determined. We're going to start AVL, which is, in my opinion, a more sophisticated software, and an even more sophisticated and in-house software that we have is CFDS, made by Anastasia and Sharish. We will also hope to use that as well in the future when we are analyzing the flight dynamics of the aircraft. All right, questions? Yeah.
When we were at the NEAT fair, we saw various tail configurations where the rudder was the biggest surface of the aircraft, and most of the V-stab was a rudder. Did you guys do any analyses on that? And what were your thoughts?
So we discussed with Professor Demaro on the possibility of having a full control surface on the detail. I think while it may be I think for the banner, he suggested it was more static stability, like how much your vertical tail size would be when when the banner gives a perturbation or it gives any disturbance from your yaw moment, and even if you try to correct with the rudder, the banner might be at a different point, perturbing on the other side. So it's more of a case of static stability. But to answer your question, I will say that while yes, it may provide more effectiveness, we need to also consider facts like how much work do we need to provide that much deflection, and how are we going to integrate it? How is it going to be integrated into it's going to be something new that we've done to get to control it well and make sure it's effective. Other questions? Yeah.
So you guys are using a single rudder configuration, right? But have you guys considered using since yaw is an important parameter, have you guys considered doing a twin rudder configuration?
I think we a double, two rudders.
Yeah, one this side, one that side, and then just
We decided to go on a conventional tail. That is I think for our for ease of, I think based on the flight heritage, we always, since we were changing one thing of going for a biplane this time, I think that keeping everything, not changing too many things would be would be a bit more feasible for us. So we won't I'll say this, we won't know how well our aircraft will respond until we get it in the air and until until it flies. So we don't know for sure. These are all predictions, and I think an oversize of the rudder and the vertical tail is good enough for now. And what I want to see is a prototype being built very, very soon, so that we can see it fly. If it crashes, we can we can correct it, see what went wrong, look at the footage, and go on from there. But
these are the dimensions, everything's in inches.
Yeah, so for the aircraft, as stated before, we're using the airfoil MH114, which will have a span of 48 inches and a chord of 11.9 inches. And we're using the biplane wing configuration, which will allow for minimization of RSC, which we know is a very important factor for scoring. Okay, so for this year, we're going with a conventional half fuselage as opposed to a boom tail that we've done last year. Both our A-stat and B-stat use the same airfoil, which is the NACA 0015 airfoil, and it is a symmetrical airfoil. Our horizontal tail has a span of 28.26 inches and a chord of 7.07 inches, and our vertical stabilizer has a span of 13.4 inches and the same chord of 7.07 inches.
So for wing to fuselage attachment, since we have a single wing at the top, we just kind of screwed it in and attached like a carbon fiber spar through it to make sure nothing happens during flight. For the bottom wing, it's going to be split, so it's going to be like one of our previous airplanes, which was Susan, where we separately bolted each of them and had like a carbon fiber, so it's like pretty similar design of integrating it, but it's each different.
And as Parks has mentioned, since we are doing a biplane, we also need to account for bracing. And what bracing basically does is just adds stability to your plane. And this can either be in the form of solid rigid struts or also wires. Wires only act in tension, while the struts, since they are rigid, they will act in both compression and tension. When a wire like compresses, quote unquote, or just like bend a little bit. Yeah. Caveat is external bracing will, of course, since it's more in surface area on your plane, it'll add some more drag. And the entire goal of this is we need to minimize the drag by optimizing the angle between the bracing and the wing. And we found, when I searched online, it was, you want it to be 90 degrees to perpendicular. You want the bracing and the wing to be perpendicular to each other. But like from the side view, if we look at this is from the right side of the plane. We have struts that go down, that are vertical, and also we have one diagonal. The diagonal we have decided to, at least for now, just have it 40 degrees to the vertical. That's it.
Yeah. All right. Let's talk about the nose cone. First, before I go into this, I want to mention that some of these measurements are a bit tentative, and we're working on it essentially. But for now, I can tell you what we have. We're gonna 3D print this cover with, I believe, a 6.25 by 7.45 inch base, and that has a 0.75 inch corner fillet. And the propellers, the dimensions of the propeller, it's a 20 inch by 12 inch propeller.
So our landing gear configuration for this year is a tricycle landing gear. As you mentioned, we do have a lot of experience with that in the past, and it has worked out well for us. So the clearance between the bottom of the fuselage to the wheel axle is 5.5 inches, so we shouldn't have any issues with prop clearance, and all of our wheels are have a diameter of 3 inches.
So this is the firewall hang calculations. Obviously there's a motor at the center of the firewall and creates a thrust. We want to, at max thrust, it creates a stress and a strain. So I use mechanics and material equations to calculate the maximum strain using the Young's modulus as well, and get about like 0.004 millimeters of deflection. And that this also reflects the simulation numbers in the next slide. So we get about like 17% deviation. And I think I got the number wrong for the distance. consistent. After that correction, I think I should be spot on. Any questions?
Nice work to every instructor for all their work. I love the OML. I actually did it in a little 3D augmented reality simulation recently, so it's pretty gnarly. Looks amazing. So good job to you guys and all your hard work recently. So, coming up now, in order to make this mission viable structure, I'm proud to introduce the mission team up to the stage. Now, come on, folks, come on.
Alright, just introduce yourselves. My name is Joel.
Hi, I'm Jake. My name's Tom.
Hi, I'm Lorena.
I'm Omer.
I'm Zach.
I'm Ariel.
Thanks, Ariel. So, the mission team, what are we tasked with this year? So there's three sort of components that we have to think about. One is the banner deployment. So how are we going to deploy this banner? How are we going to stow it? How are we going to release it? The second are the passengers. So how are we going to constrain the passengers in all directions, all degrees of freedom? And the third is the cargo. How are we going to restrain the cargo in all degrees of freedom as well? So, next slide. Our first solution was for the passenger restraint mechanism. Now, it sort of resembles an ice tray, where you place the passengers in these cubic spaces that are constrained to the dimensions of the rubber ducks themselves. So this tray is going to be placed towards the upper 3 inches around of the aft fuselage, such that when the top loading door is closed on top of the tray, the ducts will now be vertically constrained as well. This tray is fully removable so that we can remove it during ground mission to unload the passengers very quickly. And then also, general dimensions, it's around 2 feet in length, around 5 inches width, and around 3 inches of height. These are to constrain the ducts effectively, and also we ran an analysis or calculation for how many ducts can fit in the given aft fuselage length that we have, and that amount was 18 inches, and so that's how we came about the length of this tray.
So in order to further configure this tray, we had to do some decisions around materialing, which our first idea was 3D printed, and then we wanted to go with 1/8 of an inch pylon wood, which is our standard airplane building dimensions for our aerostructuring kind of team. And that is the choice we made that because it was more easy to manufacture. And after I was done with the CAD model, I had to do some weight cutting on top of our original design. And the configuration and the orientation of the weight cutting was basically, I wanted to constrain it as much as possible from the X direction, and the Z direction kind of course closed from the top and the bottom. So I didn't want the ducts from the slip from the bottom and the top, or I didn't want them to slip from the forward, but I did cut some extra weight from the sides because it's going to be slightly tightly fit. The maximum duct length should be about 2.5 inches. I put a 0.02 inch extra room for ducts to be able to install in ground mission really easily and smoothly, but that should be able to constrain it due to our material being good and have high friction constraint. From the sides, I'm expecting that the ducts won't slip from the sides. I cut a little of extra weight, and that's the reason why we did go with this configuration where we have a single line from the middle and the right side of the cut, but there's an X on the top and the bottom and the forward direction of the ducts where we're going.
Alright, so our cargo restraint mechanism will consist of a 2-piece modular rack. The bottom piece there is our base plate. That's going to be able to move separately from our top piece, which you'll see consists of 2 separate columns, each able to hold 3 pucks each that'll stack on top of each other. This rack system that can move separately from the top and bottom will allow us to load and unload cargo very quickly and efficiently during our ground mission. And we chose 6 pucks here as per the requirements from the rules, since we have 18 passengers.
So there's some features of this guy here, we have some hinge slots, so that'll make the easiest removal from the airplane. So we have the two on the top, just to take the top part out, and two on the bottom as well, so you can take the whole thing. So this thing is going to be 3D printed, ease of manufacturing, so it can go with wood, and it's going to be a little under 8 inches long, 4.5 inches wide, and 4 inches tall. And so the next slide here, this is how this guy's going to work.
First of all, a round of applause for this amazing family. Thank you.
Okay, so this is our trade study for our banner deployment mechanism. We came up with 3 different configurations. One that is parallel to the length of the fuselage with a clamping mechanism, another parallel to the wingspan with a similar clamping mechanism, and the banner folded under the fuselage in a box with no leading edge. Our metrics for manufacturability, ease of installation for ground mission, mission 1 and 2 drag, mission 3 drag, movement restricting capability, weight, leading edge integration, and banner dimension constraint. So I think our main constraint for this trade study was the banner dimension constraint, because our first option was not feasible. It constrains our banner length, and we want as big of a banner as possible, so we want to have a configuration that can go with any banner length possible. So our second option here fit that the best.
So looking at it, of course, with common sense, we can kind of see it is more symmetrical and stable. The parallel wingspan design we come up with looks better. Not just looks, but mathematically speaking, like if you look at the cargo installation on all the way to the right, we unfortunately don't have a leading edge, so we don't really know how the banner will act, and we have to run extra testing, which is extra time and material we have to be taking cost off of if you want to design that kind of mechanism. Overall, in terms of why this banner deployment mechanism is the best mechanism, I would like to further go into why, how this works, and what kind of mass we're dealing with in flight. So, you guys heard about it, all of these I talked about it, the banner is going to be really long. If you want to go at maximum dimensions, the banner is expected to be around 400 inches, which is around 33 feet. With aspect ratio of 5, this banner is 80 inches, or maximum length, which is about 6'8". So sometimes number might not be enough to visualize something. If you want to visualize how big 6'8" banner is, our tallest team member is Federico, he's about 6'5". So if you put the banner right next to him vertically, it's 3 inches taller than him. If you want a comparison when you're leaving or getting food, you can stand next to him and see how tall he is. You know, he's the tallest member here. So when you're flying with a mini NBA player on your plane, mounted on your axle, there's a lot of problems that can come up with this. So you need to be really careful, even carrying it, forget deploying. So how do we carry this? This design is actually kind of an old cat design. What we're trying to go through right now is a more direct body connection to the banner, because we don't want to interfere with the landing gear due to the thickness and the size of the banner and the instability it might cause during takeoff. We want to connect to the body with a more stable sound structure. After we connect to the body, the string system is expected to be connected in the center of mass on the horizontal component. The vertical, we haven't figured that out yet, but we want to connect it to the center of mass, so when you release the banner in the mid-flight, we have as least amount of instability as possible due to there's no torque arm existing since it's connected to the center of mass. That will cause our stability, and then we're going to have most likely add a counterweight in one of the edges to make sure the banner is going to be flying vertical in the entire flight through. And this is kind of a best design. We don't have to, like, for example, the design we come up with in the last slide, the initial first design, needed to be constrained from both ends, so we will make sure that the banner won't slip up. Here, because we're mounting vertically, we are not interfering with any of the aerodynamic surfaces, we're not interfering with any of the lift. We can safely deploy. The string system doesn't interfere with any of the like control surfaces. In terms of speaking, like if you were to change the design, our 3 configurations where we did decide where to deploy
the banner is too big. So this is most like stable structural sound deployment mechanism you will have. The banner is expected to fly a little bit under the airplane due to counterweight, and then of course effects of gravity. So the string is not expected to be interfering with any of the control surfaces. So in terms of just taking off and being stable with flight and just releasing, and for sake of simplicity, this is the best design we can come up with so far. Hopefully we'll finalize it, but it will of course always change. We don't know, that's the engineering process.
Well said, owner. The next part of this is the release mechanism. I skipped the slide. Skip the slide again. Where's the? Oh, okay. You know what? This works. So basically, the release mechanism. I swear there's a slide link showing a picture. Oh, okay. You know what? Let me pause the video. Hold on, so you guys can see this. Here we go. Release mechanism. So where is this? What is this? First of all, the release mechanism is one thing. The deployment mechanism, which owner just talked about, is how we get the airplane, the banner from a stowed configuration to like actually getting towed behind the aircraft. Now the release mechanism is how at the end of the mission 3 you cut the banner off of the aircraft. So it's servo activated and it's mounted as far back on the aft fuselage as possible. It's an external mechanism. So this like gray piece is going to be under the fuselage externally, and then the servo activation is going to be internal in the aft fuselage. The way it works is the servo linearly actuates a pin into a loop that holds the banner up. So now our dearest Jake made a great animation to illustrate this. So as we can see, linearly actuating pin here so that the banner, the free end of the banner that has a loop can just fall out, and then we activate it again, and now it's secure in all directions. So for the animation, you guys know what to do. Round of applause. Yeah. Okay, so next, banner material. What are we going to make our banner out of? This we did a trade study for. It was actually a pretty interesting trade study. We kind of conducted it in a way that we haven't done before. So usually in our trade studies, we rank our options 1 through 6 in a sort of qualitative analysis. But for here, one of our members had a great idea of normalizing the scores and ranking them quantitatively instead. So to further explain what I mean by this, let's look at the first parameter of cost for these different materials. The highest ranking score of 10 was the woven propylene, and to get the full area of the banner that we're trying to go with, the cost of the material to acquire all of that would be about $24. Now, on the other hand, the 1/8 inch LDPE, to acquire that much area, it would be upwards of $550. So obviously, we're really not trying to do that. So if we did a normal trade study, the point difference between $24 and $550+ would only be 5 points. Whereas here, the woven propylene, rightfully so, is 10 times as highly scored as the 1/8 inch LDPE. So by doing this sort of quantitative trade study, you're kind of evaluating each option to its actual individual strength rather than a relative qualitative scale. For some things, we didn't go qualitative analyses because we're not really in terms of time effectiveness, we didn't go with analyzing the skin friction drag coefficients of each of these materials. We were kind of just looking more, observing visuals, like seeing the surface roughness and the surface pass-throughs. And then also manufacturing, we had the kind help of Zach and Mr. Gardina to help us kind of go over and have a discussion about what sort of manufacturing techniques we would use and decide which material would be better in terms of that.
Thank you. So as you see here, this is our trade study for the banner material research. Of course, we were able to decide as ripstop nylon. As you can see here, it had mostly a lot of high scores in this. And the way we calculated those scores is that we used a normalized cost equation. So we found basically maybe, let's say, ripstop nylon was a score of 9.02. That means it was for woven propylene 10, which of course had the cheapest cost, and then the score of 1 to low density polyethylene, which had a score of 1. So in between that, we were able to use normalized cost equation, which I will go over later, to find each and every value in a quantitative manner. For drag and manufacturability, however, as was mentioned before, it was taken by a qualitative method in which we were not able to preferably find a quantitative or a value at all for it. So instead of ranking it by calculation, we calculated it by our own analysis and individual input and research into it. Furthermore, we were able to judge the weight for it, cost, of course, 0.1. For the qualitative methods especially, we decided on a weight of 0.1 since it, of course, was less based on quantitative methods instead of it was based more on quality than any calculated values. And I would like to preface this, for all of our calculations in terms of quantitative values, we were able to use multiple constants, such as cost, weight, using estimated values, anything from we found from constraint analysis to banner material research. And of course, during banner material research, I will pass the microphone over to Zach to go over the initial banner research.
Thank you, Ariel. So, where did all of these numbers come from? So we started with looking at a similar competition. A few of us are now familiar that DBF 2020 had a very similar premise with a banner towing component. So we started looking there. We analyzed some of the top 3 reports, see what materials those teams kind of considered, and we kind of looked into what materials do actual banners on some of those planes, like the Rutgers athletics planes out there on the football game days use. Some qualities that we wanted to assess were the costs, because we don't want to be spending upwards of $500, $600 on 1 square meter. Since we don't want our banner to tear very easily, we wanted to make sure that our yield strength is very good. And for drag, since this really isn't something we calculate heavily, this was more of like a eyeball it. Is this a rough looking material? Is this something with a lot of gaps? But all of these qualities were something that we needed to consider in order to come up with these values you see here.
Implementing all of these factors into our figure of merits, we were able to find scoring for each and every value. We used a normalized cost equation for scoring, as you can see here on these 2 equations in the middle of the really big, a lot of numbers on these charts. So we used those 2 equations, a lot of them dependent on, since they were dependent on quantitative values, you'd find maybe if you want a higher score depending on the cost, so if it's a cheaper cost, it would be given a higher score. So we were able to use the normalized cost equation to calculate each and every value. We utilized we found all minimum and maximum values for each and every category, plugged it into the equation, maximum and minimum, and then we found the value for the average for each category, and then we were able to find the score for each using that value. And going back to quantitative analysis, that was the method we used for most of them, except for drag and manufacturability, which were of course scored by a qualitative method. And because they were scored by qualitative method, we had to research more into them instead of ranking them by value or number, and that meant we had to go into more further research and also having us go into makerspace machinery and researching what machinery was compatible for the banner material that we wanted to use.
Thank you. So, since one of the requirements for the mission is to have our university logo and name on our banner, we need to find a way to very quickly get our logos on this massive banner. So, something we need to consider was, are those machines easily accessible to us? Are they easy to use? And are they, most importantly, compatible with the materials we are going to consider? So the ones that Sean and I discussed, you'll hear from Sean a little bit later, were the heat press machine, which if you were wearing a t-shirt, a lot of your t-shirts are made this way, taking an ink print and putting the paper on top of some sort of fabric, putting the heat press down and transferring that ink to the fabric. Two other machines we considered were two different vinyl cutters, a desktop cutter and a Select Cameo, which are two different types of vinyl cutters, and the UV printer, which directly prints a special type of ink onto materials. So the reason why you see that none of these materials are compatible with the vinyl cutters is that a lot of vinyls don't really tend to stick well, especially in high loading scenarios. So that was immediately ruled out for a majority of our materials. The UV printer, it is compatible with two of our materials. The only reason why it's not any higher is because the ink sometimes is not compatible with certain materials. Sometimes you need a different type of ink, and we don't know which ink the makerspace uses. This is also a less desirable material. This is a less desirable machine because it directly prints onto the fabric, and because of this, it prefers to not be bent or rolled up in any sort of capacity. So for some of our applications, this may not be the most ideal application. For the heat press, since it directly transfers ink into the fibers of the material, this would be the most ideal and is found to be compatible with 3 of our materials. This is also a machine that has been used in the past by some of the clubs that I work with, so there is some literature on this, and we found that heat press machines have been used on these materials for projects online.
Thank you, Zach. I think that's all. But yeah, I just wanted to say this sort of trade study is like probably my favorite trade study I've taken part of. I think it's definitely something we could look into for the future, kind of having like a quantitative, mathematical way of evaluating our options. So wherever you are, Jason, thank you for this idea. But yeah, any questions? No? That's how I prefer it.
I have a question. Is it okay if I ask a question about the cargo, the container that you're using to store the cargo?
Sure.
Why did you create holes on the side, even though the box will only be loaded vertically?
Yeah, the holes on the side are mainly for weight saving, like your standard weight saving cuts, and then also they double as like finger holes. So obviously you have to like pull out the pucks from the side. Yeah, thank you, Jake. Yeah, so they double as finger holes. Oh yeah. Oh, you're talking about the rails on the side, or like the
rectangular holes up there on the side.
On the side, right?
Those guys. Yeah.
Yeah, weight saving cuts. Yeah, weight saving cuts. If you meant like the one on the front face and the side face, it's because of it's like a pull-out rail system, so it needs those sort of indents to sit on the rail. I hope that answers your question.
Thank you.
Right there.
Why would you need 2 different pieces for that?
So if we go back to the animation, or actually if we explain it regularly first. So when you pull out this piece, right? This is right now 2 trays. When you pull out both of them simultaneously and you load the cargo in there, you'll see it can't fall through that bottom floor because obviously those weight saving cuts aren't enough for a puck to fit through. But when you only pull out the middle tray, so first to start the ground mission, you load in the pucks, right, and they sit on the floor. Now when you remove it, it falls through the circular holes of the first tray, right? So when you only remove this top tray, then like you could very easily just unload and drop all the cargo out of the fuselage. Does that make sense?
Wouldn't that like get jammed pretty easily, the pucks?
I mean, well, if it's tolerance correctly, 1, and then 2, like they won't drop out until the hole is like fully outside, like fully Yeah, like it could happen. Yeah, like it. Like
Pulling you out, is gonna get jammed?
Yeah,
Right.
There's like the hex on the bottom plate, so like if it's like,
It's like
yeah, if like a puck gets like stuck in those hexes or something.
oh, okay.
It could happen.
Yeah, we'll look into that. Thank you.
We'll have to test it and see.
Yeah.
Maybe we'll sand it down. If it's smooth enough, it shouldn't be a problem. If it's cold enough, big enough for the puck to get stuck on, but it doesn't have like a uniform surface, it's pretty smooth surface.
Yeah.
It shouldn't be full. And if anything gets stuck, I'm pretty sure we can like manually push it down. Like if it does get stuck.
Yeah, I'd like to know, for such, when you, in the diagram, at least in the animation that you're seeing, you're loading, it looks like the part is a full cut through for the pucks. So, my question is, how are they getting locked into place?
Yeah. So the top tray is a full cut through, but that bottom tray isn't a full cut through. Like I don't know if you can see there, like it's a honeycomb structure, but like the pucks can't fall through that bottom tray. So that's how they're held into place, at least vertically. And does that answer your question?
Do you load them from the top in
Yeah.
case the bottom is blocked? Because if there's a surface, there has to be a surface there holding in.
Yeah, you pull out both of the trays and then you load it in from the top. Yeah.
Okay, yeah, that answers my question. Thank you.
That's okay.
How do we make sure the banner is stiff when it's being held by the claws?
Banner's stiff.
So it's not floppy on the end. Like it won't slip off when it floats.
Okay, it has a leading edge, yeah. Like it's all attached to a carbon fiber leading edge, so
Okay.
yeah.
Will that leading edge just fall out of the sky? Or will it be attached to the banner when it unfolds?
It'll be attached to the banner, yeah.
Okay.
Yeah, the leading edge is there for like the banner's structural stability and the banner's aerodynamics. So like the banner
You're
needs
gonna
it.
fly with bleeding. That's it. You don't want to fly without bleeding. You're not bleeding that. Gotcha.
Yeah. Any other questions? What's up, Sean?
I want to bring it back to the hockey puck thing.
Yeah.
So how are you guys going to make sure that when you're loading the hockey pucks, you have 6 of them in there, that the bottom plate doesn't accidentally fall out of your hands while you're trying to load it into the plane? Because it doesn't look like it attaches them all to the
Yeah, well, it wasn't in this like OML model, but we'll have a stopper so you can like pull the bottom one at least completely out of the plane. Yeah. Any other? Yeah.
Is there anything like stopping the pucks in the top tray from like falling into the front tray or no?
Falling into the bottom tray. Like so, if we look here, this is the bottom tray here, right? And it's a solid. Well, it's a pretty much solid surface. Like these holes, these weight saving cuts are not big enough for a puck to fall through. So you can just think of this as one solid plate.
Only the top, like if you had a stack of pucks and then you put a puck on top, would it fall all the way down? Or stop at the second floor?
It's stacked on top of the other puck.
Yeah,
There's no
it's-
floor, it's just kind of like Pringles in a can, just stacked on top of each other. The puck is stacked on. Yes. Yeah. Like Pringles.
So the banner is, from what I understand, the banner is launched along the x-axis. But
Yeah. Wait. Say that again. Sorry.
the banner is going to be launched like this,
It will be started parallel to the wings.
and then it's going to turn. So it's parallel to the stabilizer, or maybe vertical stabilizer.
Yeah, like once it releases, there's a string that connects to the aft, such that when it releases, it'll just like be at the correct orientation once it releases.
Yeah, I could mention that once we release it, we are expected to put counterweight only on one side, so that the banners, like one side is heavier and it goes into vertical orientation in midair. So we're gonna release it from this configuration, but with counterweight pulling the weight down, it's gonna go back. It's gonna go into vertical configuration, and it's also gonna make so that the banner flies bottom of the airplane, so the strings don't get into any of the control surfaces, like the wing control surface or like the tail control surface, which should be right into the one.
Okay. Yeah. Alright, and that'll be the last question, by the way. If you guys have any other questions, please feel free to drop it in the mission team chat, mission design on the Discord. And any of us will answer the questions then. We do gotta keep it.
Or this Google Docs. There's a Google Docs.
Or the Google Docs. Alright, give it up for
It's a 20 by 12 inch propeller. So how did they deliver on each of the three engines? So first, since we're using a 3300 milliamp hour ASL, which is 97 watt hour. So that's well under the 100 hour limit. So that's a check. Limit 2, mixed flight time of at least 5 minutes. So we got 5.4, that is comfortably over this limit. So another check. And limit 3, ideal TW ratio 1.0. So how much did we get? Turns out 1.15. Just to give you a sense of how big that is for reference. So here are some of the aircrafts. So our CA-26, as per ECAL, is 1.15, and the Boeing 747 jumbo jet is only 0.27. The fighter jet F-35A is 0.87, and so yeah, 1.15 is easily like we can probably do some pretty damn cool maneuvers with it. So that's another check.
So we also did a lot of variations with our propellers. So you can see here that we have a 20 by 12 propeller, and we have a bunch of different variations for KB for our motor. If you notice that the higher KB that you have, the more thrust to weight you have, but also you're compromising on your flight time. So we went with somewhere in the middle with the 220 kV motor, where you can see we have a flight time above 5, but also have a thrust to weight that's the highest possible that we can get. So there's some graphs that we made. Here it's just another visual representation of the higher RPM is, generally the higher your thrust and power are going to be. Here RPM also corresponds to the kV of your motor. So this is basically just a comparison of just an overview of what our propulsion system we've selected is, and also a comparison to last year data listed. You can see that we had 16 by 10 inch prop last year, and this year we have a 20 by 12, so considerably bigger. So next with our battery, we have a 33 milliamp hour 8-cell battery, and we have a 120 NBSC. And our motor is a 220 kV motor, and our propeller is a 20 inches in diameter and 12 inch pitch. And the propeller spins. So I don't know what this is. Oh, it's gone. There was like it said spin and then a thumbs up. But it's gone now. But that's okay. But yeah, that's all we have. Thank you.
Can I ask a question?
All right, thank you very much, Propulsion. Thank you for the very cracked work. I'm actually really happy about this propulsion configuration because there's going to be a lot of crazy maneuvers that are going to happen for this competition, and this is probably one of the most difficult competitions we have yet to perform in. So props made, massive props to Propulsion. So thank you so much, guys. All right, and now to actually have the aircraft fly, we first have to build it. So let me hand it off to manufacturing.
Thank you, Anastasia. So, first off, we're going to give you guys just a brief overview about our manufacturing process and what we're going to section off our time as during the year. So right now we're currently in phase 1, which consists of a lot of materials research. Because although we have some methods and materials that we're very familiar with, that we've used in previous years, that are very tried and true, we will always want to look to improve, whether based on the specific missions that we have, or just generally for the club we have processes that we want to improve upon. Then once we have an initial CAD, and we can then start manufacturing a initial prototype, is when we move into phase 2. And that process sees us going through multiple iterations and fixing any potential issues that might arise, figuring out how well our aerodynamic calculations are, and then once we get very close to the actual competition time, and we, what I like to call crunch time, we begin phase 3, which is creating our final iteration that we're going to end up sending to the competition. So So this is just a little flow chart to give you a better visualization of the overall process of creating a design, testing the design, improving upon any designs, and then finally creating the final aircraft. So right now, we finished preliminary design. Now Aerostructures will be moving into creating a CAD model, and we'll be doing some subsystem testing and further prototyping along with the mission team, and then we'll then go into actual manufacturing. Okay, so for phase one, we have a bunch of slides that will show you our research that we've been conducting.
So the first fiber that we've really been looking into working with was carbon fiber. But one of the biggest things that we have to worry about when working with carbon fiber is the safety concerns. When you're working with carbon fiber, as you may know, there's the fibers float around in the air, and these can cause a lot of irritations to like your eyes, your skin, your lungs. So we kind of like pretty much have to work with different like respiratory protectors, eye protection, gloves, and like skin protection, just to avoid all of the different like hazards when working with carbon fiber, because that could be a problem when you're doing like all the different types of layouts.
Alright, so the two main ways you can make the carbon fiber is first 3D printing, which is the easier way, because it's just more readily available. Or you can do a wet layup, which is a process where you lay down carbon fiber in a certain order, and you wet it using epoxy, and you have to make sure it's completely wet, because one of the downsides is that it bubbles, and the bubbles make it less strong. So you have to make sure no bubbles. And then it's got to sit for a long time as well to cure because of the epoxy. So the 3D printing is easier, but the wet layup is also a good alternative. So we also have researched some natural fibers. As you can see up here, we look at flax, hemp, jute, and kentha. And the one that we have, flax is the one that would be the best for us, because as you can see, it's strongest. It's also most readily available. The processes for laminating it are similar to that of carbon fiber. As you can see, it's the layups. And we can't do the vacuum because it's difficult because of the equipment we do not have at the moment.
We do have like vacuum bags and like, but we don't have the autoclave. We don't have the autoclave.
Yeah,
But
no
we can do
autoclave.
vacuum stuff.
We can do vacuum stuff, no autoclave. Sorry. So the natural fibers are not as strong as carbon fiber, but they're easier to work with and less dangerous. There's less safety precautions you have to take. It's more just being careful. And the main parts we would use the fibers on are the reinforcement parts, where the wings connect to the fuselage and the motor connects to the fuselage, and also just various mounting parts. It is also much cheaper. Carbon fiber is kind of expensive.
Yeah, also just like one more thing to add to the carbon fiber slide, if we can go back to that one. So one of the like strengths with using carbon fiber versus the natural fiber, it's very rigid, so it has a very strong tensile strength, so it can resist like very strong pulling forces on it. But it's very brittle also, so it'll snap really before it bends, which can be a problem, but it's also kind of a good thing sometimes. And then when it comes to the cost, like the 3D printing, like as we said earlier, it's a lot easier, but it's kind of really expensive. I mean, you can see that it's kind of a lot to print. So it might be a little bit more cost effective to just get the sheets and do the wet layout than do the 3D printing. And then you can go back to the epoxy. So for the epoxy, it's for the safety wise, it's very similar in concerns to the fiber, except instead of like actually fibers being in the air, it's more like fumes and stuff like that. So you don't really want to be inhaling that or getting that on your skin or eyes or anything like that. So we'd be using the same type of protection when you're working with the epoxy that you would be working with the carbon fiber. And the procedure, the application, we mentioned it a little bit before in the wet layout, but you can do it with like sprays, brush, rollers, and you just want to make sure that you wet the entire piece of carbon fiber, like while you're doing it to avoid getting like air bubbles and pockets and stuff like that. But the main reason we use epoxy as opposed to like because it holds it together really well, but it also adds to like the strength of it. So it'll bend a lot easier. Not the carbon, but like the epoxy will bend before the back breaks, doesn't stiffen up like that, as you can see because of the Young's modulus. It's very high, so it'll bend pretty easily. And then our two different types of resin that we were looking at. One was the epoxy, which it's really light, it's strong, but it's really expensive. And then we have the vinyl ester, which it's like a medium price, but it's medium strength, so it's kind of like a trade-off. It's more cost effective, but it might not be like exactly what we need.
So another important material to consider in this is aluminum. So before I mention the alloys that can be useful for our RC aircraft, I first have to go into the hazards. So while aluminum in itself is not a dangerous material, it should be mentioned that in large overdoses, either through inhaling it or through contact with the eye, it can cause respiratory issues and burn in the eye. So how can we solve this? Easy. Use eye protection and probably dispose of it whenever possible. And also wash your hands immediately after exposure to the aluminum itself. So when going into aluminum, I decided to go and research on aluminum in the 6000 series. What is a series? Well, from aluminum alloys, a series refers to the primary elements that is involved in the alloy itself. So in this case, the primary elements are magnesium and the potential uses for aluminum in this case can be for the fuselage and firewalls. Why is that? Well, for the fuselage, for instance, it provides a pretty good strength to weight ratio, which can in turn improve stability of the whole aircraft when it flights. And for the firewall, it acts as a protective barrier and is lightweight. So so not only is it lightweight, but it can also protect against external environmental problems, including UV radiation, which can cause corrosion within the internal structure of the aircraft. So by using aluminum as a firewall, it can help prevent corrosion within the interior. And three types of alloys I looked into for aluminum were T4, T6, and T651 in the 6061. So while these types of alloys are quite similar in terms of their properties, it ultimately comes down to how they are produced that ultimately defines what they are. For instance, for T4, it is the most basic to produce out of the three alloys, while T6 and T651 are more complicated. Why? Well, for T6, it goes through a process on top of how T4 is made, but it also goes through a process called artificial aging, which is basically you heat up the metal in order to increase its strength and hardness. And for T651, not only do you do all that, but you also go through a process called stress relief, which is basically stretching the material in order to relieve any internal stress within it. This in turn helps with stability. And by researching, I found that the best type of alloy was T6. Why is that? Well, it had good properties overall. It was had good tensile strength compared to T4. And while it was not as while it did not have as much tensile strength and stability as T651, considering our budget, and also because T651 is way more expensive because of the stress relief stuff that's required, it will be needed to consider, and thus T6 would be the best option for us.
So next we're going to talk a bit more about foam. Something that we like to consider is one, safety. So mechanical ventilation was really important to us, and standard PPE as well was really important. Some things for the usage for foam is like securing the payload. Obviously we want to make sure that the payload doesn't fall before it needs to, so securing it with foam also makes sure that nothing happens to the payload while the aircraft is in flight. Including that, we're going to cut foam using either an electric knife or a CO2 laser cutter, which is provided by the makerspaces at Rutgers. We consider considered a polyurethane foam. The only problem we found with that is that when you cut it with a laser cutter, it releases hydrogen cyanide gas, which obviously is not good and wouldn't be allowed by the makerspaces either. So we switched to polyethylene foam. Polyethylene foam is the same foam that you can find if you ever open a toolbox and you have where your tools are placed. That's basically the foam that they use to surround it. The density is also pretty light as well, with a pretty high compressive strength as well. Other than that, we also have XPS foam, which is insulation foam. I believe the foam is called polystyrene foam, and again, density is pretty high, and the compressive strength is also pretty high as well. The only thing with XPS foam is that it has permanent deformation, so that if you ever were to hit it or anything like that, you cannot get it back to its original state. Polyethylene foam is more likely to go back into its original state once hitting it.
Alright, this is going to be phase 2. We're going to be doing more trade studies, so you've seen plenty of trade studies in the previous slides. I don't need to explain it too much, but basically we get figures of merit, we weigh those figures of merit, we list the options available, and then we make the scoring for them. We're going to be doing a lot of trade studies in the future for materials and different parts of the aircraft, but it's going to come out more once final configurations are released. So we're going to be doing more research. So some researches we're going to be doing are on adhesive additives. So some things we found already is that baking soda can be used as accelerant, and graphite powder can strengthen CA glue. And some epoxy additives you can see right there. That's peanut butter. Just kidding, that's wood flour thickener. And then we have some silica powder, which will increase the durability on it. Phase 3. Phase 3 is going to be the final assembly. That's from last year, us all manufacturing data lists. We're going to be putting everything together that we learned throughout the semester, all our research, all the CADs, all the mission design. We're putting it all together. We're also going to be keeping manufacturing logs for everything we do. Anyway, that's about it. Any questions?
that complicated?
Sorry.
So she was talking about like doing research on scale. So maybe it's not that complicated. I'm sure that people have done it. So you just have to look at what they're doing, match the Reynolds numbers. Match the Reynolds numbers, scale fast.
happening in 7 days. So I was like, oh, 7 days, we should maybe go to this. Called up the organizers, a very cool guy. Apparently he knows about the DBF stuff. And he told us that there's going to be a lot of cool RC aircraft veterans and like flight enthusiasts and stuff like that who can mentor us and be very happy to talk to us and learn about what we do. So yeah, there were in fact a lot of friendly people. We drove out about 3 hours to upstate New York and to a place called Peaceful Valley Campsite, where they had like hundreds of RC aircraft flying about. We had about 18 total attendees representing the Rutgers AIAA chapter, so that's between RPL, RU Airborne, and RU Auto. Again, encountered a lot of friendly, curious RC flight enthusiasts. They asked about our plane. They were like, nice. They're like, oh, it's nice to see the kids not like wasting their time on TikToks and whatever the kids these days do. So yeah, we secured partnerships with very nice and like knowledgeable people. Like for example, we have the contact of someone who mentored MIT to a winning competition season 1 year, and then also a bunch of other people who know about DBF. We got gifted free stuff like LiPo battery charging packs, electrical connectors, free artwork even by very nice vendors at the location. And also we got like free admission and free pilot registration as well, just because we're students. So shout out to those guys. Tom Hunt, I know you're watching. No, I'm kidding. Yeah, but yeah, we saw a lot of cool, wacky aircraft. As I was explaining to Lorena and owner. So like that aircraft on the top there, I don't know if you guys know what wing warping is, but basically like early aircraft before control surfaces existed, the way they turned was by physically pulling one side of the wing up so that the aircraft will roll. That's before like control surfaces like ailerons and rudder existed. So this guy went and built that in a scale RC model. He did RC scale wing warping to turn the plane, and the plane flew, and it was very cool and very insane. I also didn't include a picture, but there's a flying skateboard. Yeah, and like Snoopy was the V-stab, and then it flew like stably, so that was very, very cool. So yeah, very nice connections. I hate this picture because they always use and post this one, and also one person not paying attention. But yeah, no, very, very nice connection secured. Yeah, and we'll definitely be coming back next year and hopefully flying one of our own aircraft there to impress and gain more exposure and things of that nature. Thank you.
Alright, just to wrap up this evening so we can sign off real quick. We got a couple things about sponsorships. I know that's the fruit of the labor for everyone here working. So, sponsorships. I don't want to yap about this. How about I let the guy who actually got the sponsorship? Adrian?
Alright, so over the summer, we work on to getting a couple of sponsorships to... Okay, so over the summer, we did a lot of work to get a couple of sponsorships, and one of them was pretty special, as this year we are getting sponsored by Barada Controls, as they are the main sponsor of today's competition, or this year's upcoming software competition. As they are giving us $4,000.
Thank you very much, Adrian. Thank you for everything. And additionally, I'm talking to Professor Peru right now. We have some future stuff with NASA cooking up in the works. So hopefully we have either more material or monetary sponsorships from NASA. I know we're going to definitely use our connections with NASA and continue building the bridges. So that's in the talks right now. So I'll have more news out as soon as possible when I finalize stuff with Professor Peru. So shout out to Professor Peru and of course our advisor, Professor Demaro.